Welcome back to Chapter 7. We're going to talk about SN2 versus SN1 in much more detail now. SN2, SN1. Kind of introduce these topics or these concepts. Now we're going to talk about them more. So we're going to show two mechanisms for nucleophilic substitution with the same nucleophile. So we're going to look at R, BR. We're going to talk about the R in a minute. We're going to use sodium acetate. We'll talk more about the nucleophile later. We're going to use sodium acetate because it's a nice moderate nucleophile, and we can talk about SN2 and SN1. And so we're going to see this reaction, and we're going to get an OR bond. And there's another reason we get sodium bromide. It's a negatively charged moderate nucleophile. It's really a perfect teaching nucleophile. And so this is the product we're going to get, and we're going to talk about two different R groups. Okay, we're going to talk about the extremes here. So let's draw it this way. CH3 sodium acetate, what it's called. It comes from acetic acid. And what we're going to see here is that bond making is competitive with bond breaking. We gave these in generic terms before. This is going to come in here, and we're going to see that this is not very sterically hindered. Okay? And there's a bond there between the CH3 and the BR, and we're going to see that we're going to go over this mechanism over and over. The CH3, this carbon-bromine bond is breaking at the same time that this carbon-oxygen bond is forming, and we get CH3, CH3 over here, the O CH3 bond formed. So new bond. Okay. The rate of this, because both are participating, the rate is the concentration of both. Use OAC for sodium acetate. That AC is this whole thing. Okay, acetate. This is second order bimolecular. Second order bimolecular, those are synonymous. Okay, this is not sterically hindered. So this is SN2. Like I said, we're going to go over this and over this. The other one, we can use sodium acetate as well. Is we're going to look at a butyl bromide. Carbon-bromine bond. It's going to form, I'm going to put the product over here for a reason. We're going to form a very similar looking product. And the same byproduct. But the deal is, this is I said, is a moderate nucleophile. And this is a very sterically hindered. Very sterically hindered electrophile. Okay? Electrophile. Sorry for the delay. So very sterically hindered electrophile. And what that means is this can't get in there. Okay, what we drew for the SN2 is not true for the SN1, but what can happen is that this can leave. Okay, so bond breaking is much faster than initial bond making, and you form a carbocation. I said this is the most important intermediate, plus Br minus. Carbocation dissociates. The CBr bond dissociates. Okay, it's a dissociative mechanism, and the carbon and bromine bond break. And so then what happens is after that happens, this is an electron deficient carbon. We're going to show this carbocation even more. Then you form the product. So the rate of this is only dependent on the concentration of tert-butyl bromide. Okay. And we're going to repeat this in so many ways, so it'll feel like we're going fast at first. But this is step 1, slow, rate determining step. Step 2 is fast because carbocation is electron deficient. They have empty p orbitals. It's going to attack. So let's dig into the SN2. 7.11, I believe, is the SN2 mechanism. Again, we saw the overall reaction. Okay, we have sodium acetate. I'm leaving off some lone pairs. CH3Br. We form a new carbon-oxygen bond. And we get sodium bromide. Okay. This is kinetics. Again, we have observed these things. These over decades. These are observation, and these are the kinetics. They're second order. I'm just going to say these things because I'm repeating them. Bimolecular, okay, I mean 2 molecules are involved. That's where we get SN2, second order. Okay. Both the electrophile and the nucleophile are involved in the rate law. It equals, again, to see that, CH3Br times sodium O acetate. So changing concentration of either reactant affects the rate, right? If we double the concentration of this, we double the rate. If we double the concentration of both, we quadruple the rate, okay? So it's just some simple math. Those kinds of math questions might be asked in terms of simple multiplication or whatever, not calculator math, okay? So that's kinetics. So how do we make sense of this? A concerted mechanism best explains the data. Okay, this is our theory. We can't get in there and see the molecules do this, but this is our theory to explain the kinetics. So what do we mean? We have a carbon-bromine bond. We have sodium acetate, and this comes in from the backside attack. The exact same time the bond is forming, the bond is breaking. So this is how we show it with arrows. Again, the same product is forming. We have sodium bromide. Okay. So we can describe this transition state now, not an intermediate, but we can show the transition state like this. Carbon is tetrahedral, but we're going to think of it as 2 half bonds. So in a sense, the transition state is sort of trigonal pyramidal. Okay, these H's, these 3 H's are all in the same plane. Okay, this H is coming out towards you. This H that I've squared is in the back. Okay, we have simultaneous bond breaking of the bromide. One of those pairs of electrons is in that half bond, and we have the oxygen attacking brackets, and we put a double dagger. That double dagger indicates transition state. One more thing, partial negative, partial negative. Notice we had a full negative charge on oxygen and a full negative on bromide. In the transition state, that single negative charge is shared over the 2. All right. So let's draw an energy diagram for this. Again, we showed general energy diagrams in chapter 6. Energy reaction coordinate. Here's our starting materials. This is an exothermic reaction. Same thing, sodium acetate, CH3Br. What do we get? We get sodium, we get the ester. Okay, not sodium, sorry, the methyl acetate is what we would call it. So instead of sodium acetate, we call it methyl acetate, and of course, sodium bromide. What do we have here? We have a single step. We have one activation energy, E sub A. That is the energy barrier. That's the energy to get over the hill. The activation energy is a kinetic term. Okay, that's the amount of energy needed to put into this reaction to get to the products. Okay, this is the thermodynamic term, delta H. Okay, it's exothermic, so it's downhill. It doesn't matter if reaction's downhill. If this EA is too big, it'll never happen. That's what catalysts do. They lower the activation energy. There's no catalyst in this reaction, but just to remember that. Okay, so concerted, single step, in concert. Everything's happening in concert. One step. Now, some more data that we see, building on Chapter 5 in stereochemistry, is the stereochemistry of this reaction. Okay, so there's two possibilities. What we're going to do is use deuterium to give us what we call a primary alkyl bromide, but now it's a chiral center. There's 4 different groups around carbon. Deuterium is just heavy hydrogen. It's got an extra neutron. It is, that way we have a chiral center, okay? So there's 2 possibilities. The nucleophile can come from the front. What would that give you? D, nucleophile. Okay, retention we call this. Meaning if you, retention. The bromide is on the right and the nucleophile is on the right. Everything else has stayed the same. This is not what we observe. What we do observe is the following. Nucleophile comes from the back. It lines up opposite. Why does it do this? Because of charge. There's a dipole here, right? We got a partial negative on bromine. You got a negatively charged nucleophile coming in, so they're going to repel each other from the front. That's why this does not happen. They're repelling each other, and the farthest they can be away, like Vesper, the farthest these can be away is 180 degrees. That's the transition state. And what happens is this then leaves, and these sort of this stays in the front, this stays in the back, and they're like, think of an umbrella. It's sort of flopping to the right. Everything's going from the left side to the right side, and we're going to draw it like this. So the H is still in the back, the methyl is still in the front, the deuterium is still sort of down at the bottom, but they're all on the right side. Okay, if you calculate R versus S, you can see this, right? You could do a practice. You could have a bromide be the nucleophile. And so NU would be Br. You'd have opposite enantiomers there. Okay, so R and S, these are enantiomers. Okay, only inversion is observed, only product in SN2. All right, we're going to see that SN1 is very different. All right, so what's our explanation? I said this all verbally. I'm not going to redraw the reaction, but let's draw the transition state. This is the transition state for the reaction we just showed. Highest energy species. Here's the nucleophile. Here's the bromide. Delta minus. Put in our lone pairs. Double dagger. Okay? So it's attacking from the left in this case. And the bromide's leaving from the right side, the front and the back. These deltas are 180 degrees apart. So a couple examples. Now we're going to do it in a different plane. Put a chloride. And use sodium hydroxide. Since it's backside attack, it's coming from the back here on the opposite face, the back face. And what do you get? You get only one product. You get inversion. Inversion, inversion, inversion. SN2 equals inversion. Of course, you get sodium chloride, okay? But you get inversion. This is a secondary. We're going to see that this gets a little more complicated with elimination, but we're talking about substitution products right now, okay? Because sodium hydroxide is also a base, but we're focusing on substitution, okay? Let's do another couple examples. Another secondary. We're using secondaries because it gives us inversion, okay? Secondary, you can use sodium cyanide. Not something you actually probably want to try. Sodium cyanide is dangerous. But you get the back attack. Now we're doing the left to right kind of thing. Plus sodium iodide, we get inversion, okay? So I want you to memorize that SN2 gives inversion, but I want you to learn how and why. Sometimes we'll drop off the H. It has to be there, and actually I think that makes things easier. Okay, those all gave enantiomers when we gave inversion. This, let's say it's a the cis, right? And then we treat this with sodium, what we call ethoxide for ethyl, ethoxide. What do we get? We get only backside attack. Okay. This is the trans relationship. These are diastereomers. They're not diastereomers, sorry, because they're different products. But this, if there was a cis, you do not get cis. Okay. This remains unchanged. Okay. Again, we're going to do some of these examples, but you don't get cis. You only get the trans. Okay. You still get inversion. Okay. But there's another stereo center, okay? And again, we'll see. We're going to put these puzzle pieces together. We're going to see with SN1, we get a mixture of two diastereomers, and we'll explain why, okay? So let's talk about the R group on the alkyl halide, okay? CH3X, R, CH2X, R, 2CHX, and R3CX. Methyl, primary, secondary, tertiary. The number of carbons attached to the central carbon is very, very important. The most important factor when deciding between substitution reactions, okay? So these, again, you can memorize some things. No SN2 ever, okay? Or for our purposes, ever. Two sterically hindered. Okay, it's just two sterically hindered for this transition state, okay? These are the least sterically hindered, so yes, they definitely undergo SN2, SN2, and then question mark. Okay, secondaries are going to be the question mark, and they're going to be the toughest ones to deal with. So what we see is increasing rate of SN2 from right to left, okay? So it's sterics, that's great. Let's show the transition states, okay, at least for the first few, okay? We've shown these already, but what do you have when you just have H's? H's are smaller than methyls or other alkyl groups. So this methyl is the least sterically hindered transition state, right? And then if you put one R group, still not too bad. As you add more R groups, you make that more and more hindered. So methyl, halide, and primary definitely undergo SN2. Secondary gets more sterically hindered. Tertiary is just too sterically hindered, okay? And again, we'll keep talking about secondaries and stuff later, all right? So another view of this, let's take a look. If we're going to look at energy diagrams, we have CH3Br plus NaOH versus a secondary. Okay, plus NaOH. The way to think about this is we have two different energy diagrams. I'm going to show them abbreviated. We have starting materials to products, starting materials to products, right? So in the case of this transition state, what do we say? It's a low energy barrier. Okay, that transition state, we drew that on the previous slide. That is a lower energy barrier, whereas to get to this one, it's higher because why? We have two R groups in the transition state. It's just more sterically hindered. The OH and the BR. Okay, these are all in the book. You can work through these. More and more examples. These explanations are in the book. So the energy barrier is much, much lower because of the steric hindrance. Okay, so let's look at a summary of SN2 to repeat some things. Second order is also called bimolecular, meaning both molecules are involved, the alkyl halide and the nucleophile. So the rate equation reflects that. Right? We call this a concerted mechanism, a single step. And there's inversion, that's very important, inversion of stereochemistry. All SN2 reactions undergo inversion, but not all starting materials are chiral, so sometimes it doesn't really matter, okay? But they all undergo that transition state, and it's essentially inversion, okay? Unhindered alkyl halides react faster, again, because of the transition state. So you got to work with that transition state, okay? So let me give you an example of a primary where the inversion is inconsequential, okay? So we just have a substrate here with a little extra functional groups on an alcohol and an aromatic. And now we're going to add an amine, just to remind you how amines behave. Okay. Amines are neutral, so they're a little different. This is still backside attack, still inversion. And we're going to abbreviate that as a phenyl. And you get this. At least initially. We'll see it gets more complex when we get to the amine chapter. But for our purposes now, that's substitution. And you get the salt. This whole thing is the product. Okay? It's not a byproduct. You need all of it to be correct. This is inversion. Okay? Still inversion. You have two hydrogens, etc. It's just inconsequential. All right, 7.12 is the SN1 mechanism. Let's take a look at that. We're going to look at the overall reaction now. Same nucleophile, but what do we have? We have a much more sterically hindered alkyl bromide. Now, to repeat, this cannot undergo SN2. So we're going to say no SN2, but it doesn't mean it cannot substitute. It just can't proceed through that mechanism. Okay. So we'll see what the products are. We're going to form an oxygen-bromine bond, etc. We'll show that product. But the kinetics here are now first order. Only one molecule is involved in the rate equation. Rate equals K times now tert-butyl bromide. Okay? And notice this is the sodium acetate is not involved in the rate law. So concentration of this sodium acetate has no effect. Changing the concentration of alkyl bromide will double the rate. If you double the concentration, it'll double the rate. Okay, but that's it. All right, so again, we have data. What's our theory? A stepwise mechanism best explains the data. Okay, So here we have the CH3, the tert-butyl bromide, and we said it's too sterically hindered for the nucleophile to come in here. It can't get past those methyls. But what can happen is, let's say often you would heat this reaction or whatever, but the idea is, because it's a stable compound, my point is, but you put it in solution, you heat it up a little bit, this bond breaks. And what do you get? You get a carbocation. Okay, that carbocation, this is a slow step because it's not going to just fall apart. It's an organic molecule that we can get out of a bottle, okay? But slowly this happens, and now what's empty on the C is an empty p orbital. It's electron deficient. Now the sodium acetate will come in there and attack, okay? Because that's going to happen fast. This can go backwards too, right? The bromine can go backwards, but the idea is this is a better nucleophile. As soon as that forms, that's going to happen fast, very fast. What do you get? You get the new carbon-oxygen bond. Okay, that's your product. Carbocation, really, really important. So associate some things. SN2 is concerted, it's inversion, okay? SN1 goes through a carbocation. And we're going to get we're going to see what we get as racemization. Okay, we'll explain that here briefly. Okay, well, I'll tell you right now, this comes from the top or the bottom face, or the front and the back. So you're going to get two products when this is chiral. Okay, so we'll show some examples. Again, just to reiterate, right? We have a Lewis acid here with a Lewis base. Okay, every arrow can be explained. We're steeped in mechanism now, so each mechanistic arrows can be explained. So this is the rate determining step. I'm going to show some energy diagrams. All right, so let's show that. Okay, energy diagram. Now we got two steps, a little more involved here. Okay. Essentially, here's our intermediate, right? Carbocation, whatever the case is. Okay. Tert-butyl carbocation. High energy first step means rate determining. That's the rate determining step. Transition state 1 is just the carbon-bromine bond partially broken. Partial minus, partial plus. Okay. And then the second step is fast. And that is the oxygen. Okay. Again, this is in the book. Figure 7.12. All right, almost identical. So we have delta H's and all that going on. Okay, there's the delta H overall. Each step has a delta H. Just like chapter 6, look at 7.12. All right, so stereochemistry is really important here. Key intermediates, carbocation. When we draw a carbocation, it's trigonal planar, it's sp2 hybridized. What we mean is draw this nice and big. Whatever the R groups are, we're going to talk about this again later, but there's an empty p orbital. The more R groups, the more stable that is, and we'll show that later. It's a very reactive Lewis acid or electrophile. It's electron deficient. And again, the bromine can come right back in, but that's a weak nucleophile. The important thing here is the nucleophile, the O minus, is going to attack from there or the bottom equally. 50% of the time here, and there. 50-50. There's no preference. Okay? So you got to see that. Carbocations are flat. They're going to be attacked from the top or the bottom. So let's show a chiral alkyl bromide. Single enantiomer of this guy. We have 3 different alkyl groups. Review our names, methyl ethyl propyl, right? So the first step, what happens? We get a carbocation. I'm going to draw it left and right now. ethyl propyl. Okay, so you got this carbocation, and what can happen? Nucleophile can attack from the front or the left, however you want to think about it. Right. It gives two products. Boom, we get inversion product that looks a lot like an SN2 type product. And we get the retention product, we would call it. So we get retention and inversion. And the idea is we call this racemization because it makes a racemic mixture. These are enantiomers of one another. Okay, 50, 50, 50, racemic. Okay, so you can't get away from stereochemistry. You get a racemic mixture, you get the inverted product and the retained product together. Okay, so let's work on another wrinkle on this mechanism. Okay, so the mechanism is carbocation formation, nucleophilic attack. We're going to add a proton transfer. Okay, what do we mean? Let's look at another single enantiomer. Okay, so I have very similar group ethyl, and then I got a methyl, and then I got a deuterated methyl. Okay, and that just allows it to be chiral. Okay, and again, this is a tertiary. Tertiary alkyl iodide cannot undergo SN2, so it's going to be SN1. And this is a very weak nucleophile. We're going to talk about nucleophile strength. We get two products. And
Andy, I'm recording a lecture. But anytime you need me tomorrow for space, if you're allowed, whatever.
oh, I think it's full.
Okay.
Okay, thanks. Sorry, I had a visitor. Back to it real quick. So you get that product, that's the retention, and you get the inverted product. And you get some byproducts. Okay, we're going to go over this in class. I want you to work on this mechanism. Okay, the first thing that happens is you get the carbocation. Okay, so carbocation, and then you get nucleophilic attack, and then you get proton transfer. Okay, this is one I want to go over in person. Very important, but you get retention and inversion. Okay, we call this racemization. Okay, the stereocenter is racemized. Okay, so that's a good one to go over and think about, and then we'll go over it in class. So a couple examples. Again, we're always going to get neutral products. We're going to get neutral products. So you're not drawing protonated products when we say predicting products. So here, instead of water, we have methanol excess. Again, we're using tertiaries to make it very clear. We're not getting SN2. So it's going to go through a carbocation. You're going to get two products here. So let's draw them both. OME for methyl. And then you get the other one. Sorry, I'm going to draw it as a mirror image. And these two are mirror images of one another. We get a 50-50 mix. You get those products. Okay. Work through this mechanism. It's identical to the one that I left you with before. Now let's look at one on a ring. That's an ethyl group there. This stereocenter is not going to change. We're going to use sodium acetate. Remember, it's got an ester. That's what we used a lot. We're going to get two products here. This can't change. Again, we could draw it like that. That's the same thing. The H is implied. Because it's methyl, we have to show it. We get both those products. These are diastereomers. So it's not technically racemization, but we kind of use that term, okay? It's really epimerization, but you don't need to learn the term. Racemization is fine. We are racemizing that stereocenter. We get diastereomers. Okay? Again, now let's look at the identity of the R group to finish this up. Okay, we have CH3X. We have RCH2X, RCHRX, so a secondary, and then we have a tertiary. Okay. Now we have increasing rate of SN1, most sterically hindered, 3R groups. It's the opposite of SN2, okay? And now the rate is going to correlate to the stability of a carbocation, okay? What I want you to memorize, or I guess learn here, is I'm not putting the p orbitals in there, but you got a methyl, and you've got a primary carbocation. We're going to lump these two together here. We're going to call this a special primary. I'll use that term a lot, and this is primary. These two, we're going to kind of lump them together, primaries and special primaries. And so these cations don't form. Primary carbocations and methyls, they don't form, which means you can't do SN1 on them. Secondaries are going to be the question marks. And then the more R groups you have, the more stable. Okay, most stable carbocation. And again, we're going to talk about why. Correlates to carbocation stability. We have increasing carbocation stability. So a summary of SN1. We have first order unimolecular. The rate is only dependent on the alkyl halide. Okay, again, first order. If there's an exponent there, it's only one term. It's two steps, but it's first order. It's trigonal planar carbocation intermediate. Carbocations are key, and they're trigonal planar. We racemize a single stereocenter, so we get retention and inversion, 50-50 mix, racemic mixture. We call that racemization. Hindered alkyl halides react fastest. Hindered alkyl halides. So the next time we're going to talk about carbocation stability.